Right, perfect. Let me share my screen. Okay, welcome everyone. Welcome to the second class of this series. I don't know if this is going to be a series, but this is a second class and this is going to be technical. This is machine learning algorithms, supervised learning. Please let me know if you guys can see the screen and there's no interruptions, there's no black boxes, gray boxes whatsoever. So the recording goes well and there's going to be no disruption in learning. Okay, all fine. Thank you, Ash. Okay, so my name is Savik and today we're going to learn about supervised learning. And before we start, I'm going to tell you a very clear expectation what we're going to do. I'm going to use Canva for the slides. I'm going to use Jupyter Notebook for code, and I'm going to use GoodNotes on my iPad for the math. Jupyter Notebook is an application in which you can run interactive Python notebooks. Basically, you are going to run Python code, but you can have blocks. So you can run each block and you can even see a lot of graphs, and this is very specifically used for data science and machine learning. Okay, without further ado, let's start the class. So how many of you were in my last class? Let me start with a very simple question. What is machine learning? How many of you can answer in the chat? Please go ahead, write down your explanations and let me see. I'll pick the best one. Be very precise, okay? Just you know, how many of you? ML is a subset of AI, that is true. But what is machine learning? Can someone write in the chat? What is machine learning? Okay, I think a lot of people may not remember it properly, but human like brain, okay. I guess everyone just went to Google or probably ChatGPT to find the most concise answer. But okay, machine learning is when you teach the machine to learn. Simple, you teach the machine, you give the answers, you give the data, you give the answers, and machine learning will learn the patterns and it will figure out its own rule. Okay, this is what we learned in the last class. In classical programming, we basically have the data, we define the rules. There's if, else, and there's sequential progress, like after this block, execute this block. So everything is rule based. But in machine learning, we give the data and we have the answers to that data. Answers basically means we tell the data, in supervised learning, we call it labels. So basically we're telling the data that, you know what, this is what we're telling the machine learning model, that this is how a dog looks, this is how a cat looks. So we're telling the answers and then we're letting it define its own rules. Rules basically means parameters. So machine learning is going to figure out or tune its parameters to learn that data well. Okay, so one of the examples that I took in the last class was you train a model on Nike shoe sales data, and you use that model on Adidas sales data to predict. This is a forecasting model, and in this class I'm going to use a lot of technical terms, and we're going to focus on the math and the code. So please bear with me. If you don't understand something, write down in the chat. And if someone knows it, please help the other person. Okay. So we train a model with Nike shoe sales data, and we test it using Adidas sales data. So that's one of the examples of how machine learning models can work. This is just one very simple example. Before we start, I want you guys to know all these words in the yellow fonts. Features. What are features? Features, we basically mean input variables. When we are talking about an equation, x is the feature, or x1, x2, x3 to xn are the features. Labels is the output variable. So when we're predicting a binary output, if it's going to be 0 or 1, if it's going to be yes or no, so y is going to be the output variable. Training data. So these are examples used for training. So basically we have a chunk of data, and we are going to use that chunk, like the entire 100%. We're just going to use part of it, probably 70% or 80%, to train that model, and the rest of it for testing, or even we can keep some for validation set. We'll come to that later. Model evaluation. So how do you understand the data is doing well? How do you understand the model, machine learning model is doing well? You have to test on unseen data. Basically, you have some metrics for that, right? So you've got accuracy, precision, recall, F1 score. These are for classification problems. I'll come to that. For regression problems, we've got MAE, mean absolute error, RMSE, R2 score, things like that, okay? So model evaluation is also called inference. You'll hear this term a lot in machine learning or AI. Once the model has been trained, you need to do inference to understand how the model is performing in the real world and unseen data. So what is supervised learning? Anyone in the chat? We did it in the last class as well. We at least went through the basics of it. I will directly jump into an example to show you guys what supervised learning is. This is a discriminative model example, and we have the labels for dogs and cats. So we're going to tell the model that this is an image of a dog and learn this particular image. And I'm going to tell, so actually instead of, think about a very simple example. The labels are there that it's going to be a dog and it's going to be a cat. And I can define some really easy features. Don't think about an image, because in an image, you'll have to think about features like, convolutions and stuff. So let's take a simple example. Let's just say that I've got some data, and in that data, I've got the answers, Y. So Y is either dog. So I can say that predict 0 for the dog, or I can say 1, which is cat. So the model is going to be a classification model. Based on my input, it will figure out the features and it will output some data. Okay, so the output is a classification model. So if I've defined classification, I need to define what regression is. So when we're predicting a continuous variable, that is what regression is all about. And when we're classifying between yes or no, 0 or 1, hot, cold, or even 3 or 4 or more number of, ordinal data, or we've got different classes, that is a classification problem. In a regression problem, we basically predict a continuous variable. Okay, so this is how a regression and regression model or regression graph would look like, and this is how a classification one will look. So if you guys don't understand, don't worry, this is what the entire class is going to be about. So here on the left, you'll see a linear regression line being fitted on the data, and on the right you can see that this is not a linear line, but we've got a plane which is separating the green from the blue. Okay, so that's a classification. This is just an example to show you what the difference between regression and classification is. Okay, in this class we're going to learn about linear regression, logistic regression, decision trees, and random forest. All of these are examples of supervised learning. We're going to use label data. You're going to tell the model that these are the labels and we want answers. We want the rules, define some rules based on that, and then we'll give some unseen data, and then we want the answers back. Okay. So let's go to linear regression first. I hope all are on the same page with me till now. Checking the chat for a bit. Perfect. Thank you. So what is linear regression? Get your notebook because there's time for some math. I'm going to share my screen and hopefully you guys can see. Okay, is there any distraction? Is there anything that's blocking the screen? Perfect. Thank you. So in today's class, we're going to learn about linear regression. We're going to learn about logistic regression, decision trees, and random forest. And also one of the more important points which is there in the white right now is gradient descent. I'm going to talk a lot about gradient descent, and I'm going to show you guys why this is very important in optimizing a cost function. We'll come to that. So these are all the things that we'll learn today on the iPad with the math and everything. So let's start from a blank page and let's try to define some very basic things that we had learned in our school. Okay, let's start with linear regression. The first thing I want you guys to tell me is how many of you remember equation of a straight line? Perfect. Thank you, Ronak, for answering. Y equal to mx plus c. Okay. Now, what is m? Can anyone tell me? This is the slope, right? What is c? C is the intercept. And we know that, so let's learn how these slope and this intercept, how do we derive this? Okay, let's draw a line. Now in this line, let's put two lines, two dots in this line. Okay, what should I name it? Let's go with x1, y1, and let's go with x2, y2. Okay, let's make sure this is theta, and let's understand what slope is. So can anyone tell me what is slope? Slope is basically the rise over run, or the steepness of a line. Now what exactly is that? How do we calculate a slope? So we took 2 points on a line. We're going to extend it. This is theta. So m equal to tan theta. Why? What is tan theta? If this is A, point A, and this is point B, so the one which is adjacent to, opposite to A, and the one which is adjacent to A is this one. So let's understand this. Let me take a different color so you guys understand. So what is this and what is this? So this is basically the difference between this and this, right? Now this is y2 and this is y1, right? So this is y2 minus y1, and the same thing for the one on the bottom is x2 minus x1. Perfect. So I hope till here we're clear. So this is the slope of a line. What does a slope mean? Slope of a line basically means the steepness of a line or the rise by run. Okay, so let's try to move ahead, and we now understand what a slope is. These are two different points. Now can we do some little more math? Okay, so we've got y equal to mx plus c. We now know what the slope is. Let's say we want to just do a simple math, like just say m equal to 1, and it passes through -1 and -5. So what will be the equation of this line? Can anyone quickly tell me in the chat? Let's see who gets it first. Thanks, Ronak. So I'm going to first put x, which is, I'm going to put 1, and then I'm going to put -1 here. I'm going to determine what c is. Y is -5. Okay. So what is c? -4, right? So if I put here y equal to m is 1, so it will be x and then -4. This, right? So this is how you can get the equation of a line. Okay, are you guys clear till here? Let's understand why slope is so important. Let me clear this. This was just an example. Okay. let's try to understand why slope is so important and why we really are talking about slope, right? So we've got uh, the other way of writing this is, sorry about that, y equal to beta 0 plus beta 1 x. Now beta 0 is coefficient, beta 1 is the slope, this is also the coefficient. So these two coefficient basically determines how the line is going to look like. And there's one more coefficient which we're going to add, it's called the epsilon. So this entire thing will become the equation for linear regression. And we'll look into this, we'll try to understand why that term has been added. This is called the error. Okay, now before that we'll try to understand how we can use what we learned. Why did I tell you guys about the slope, right? First, try to understand what different slopes mean. So let's say I've got positive slope, so it would be like this. I've got negative slope, it would be like this. What if my model is like this? What does this mean? If I take 2 points here, y2 is equal to y1, right? So m becomes 0. So slope is 0 here, right? Now if I make this like this, here x2 is equal to x1. So basically slope becomes undefined. So slope of a line basically tells you a lot about how these data, so why are we learning all these things? Because we want to predict, we want to fit a line between two variables. Now we'll come into that. Let me take an example of, okay, let's see. Where did we stop? Let's see. Okay, I'm going to keep it on the side so there's no distraction, right? You can see the slides as well. Checking the chat to make sure. Yeah, thank you. Okay, so let's define linear regression. Linear regression is used to predict a continuous outcome variable. It's called the dependent variable based on one or more predictor variables. What we just learned, y is the outcome variable. We're predicting y. X is the independent variable. You know, single linear regression, we just have one x, which basically means that I'm going to predict y with just x. For example, I want to predict the price of a house based on its size. So I can basically have x-axis and y-axis defined as x will be the size, y will be the price, and there'll be a lot of data points, and I can try to fit a linear line with that data, right? It assumes a linear relationship between the input variable and the output variable. So this is very, very important. Okay, so let's see what we just learned. So we saw that this thing, right, y equal to mx plus c, mx plus b, whatever you want to say. Let's say that we've got the, I hope you guys can see the slide, so I'm going to explain in the slide and then I'm going to move back to the math again. Okay, so in the x-axis we've got apple quantities, and in the y-axis we've got price per kg. So if you look at the red dots, the red is basically all the points in this particular thing. But this is too easy, right? This is not something, this is not a machine learning problem. Like you definitely know that we get 1 kg of apple for $5, 2 for 10. So if I want to predict what will be the price of 7 kg of apple, you can directly say that all the data points are lying in the particular this straight line. So it's very easy to define, right? Can someone quickly define the equation for this particular? I want to make this interactive, so I know that you guys are how to use this math in coding or in building. Sorry to ask, I'm a beginner. There's a lot of ways in which you can do this, and we're going to learn about NumPy and also Pandas data frame. So you have these mathematical libraries specifically to do these sort of tasks, okay? Yes, you are right, Himanshu, and Vinod, you are also right. The equation of this line is basically y equal to 5x, right? So guys, please take note, please understand that here intercept is b, which is 0. As you can see, the line is going from 0, and then we've got these points. So how did Himanshu or Vinod do this? It's very simple. You can basically put these values in y equal to mx plus b, and you can see that the first point is 1, which is basically x is equal to 1 and y is equal to 5. So you can calculate, and b is the intercept, so basically it's 0. So I'll put 0, so basically it's 5. Slope is 5, so we get y equal to 5x. Okay, this is not a machine learning problem, but let's get into y equal to mx plus b. So y is the dependent variable which we are predicting here. I hope everyone's following till here. And please, guys, whoever knows all these things, help Neha to, I can see the chat here, so please help her out. Okay. Perfect. Thank you. Okay, let's continue. So in the dependent variable, we've got y, which is the price. Slope is price per kg, basically. Independent variable is quantity. So we are predicting the price with quantity. So we can see this is what I asked people to do. They took 2 points, quantity. So we've got quantity, model, price. Super easy one. Let's move on. Now this is where things get interesting, because we've got housing prices. We've got size in feet square, and we've got the price in thousands of dollars. So it's 100K, 200K, 300K. So you can see that we're trying to fit a line here. And in this blue line, these x are data points. So we have taken a few data points, and theta 0, which is basically b. So there's a lot of ways in which you can write it. So y equal to beta 0 plus beta 1 x, or y equal to theta 0 plus theta 1 x. These are just name, so don't worry about that. So these are two different parameters, right? One is the slope, one is the intercept. So theta 0 is 80 here, and theta 1 has been calculated 350 minus 230. I hope this one is clear, because you can see this 2 dot lines. 350 is x, 230 is x. So that's, sorry, y. So y2 minus y1 by x2 minus x1. So we'll calculate theta 1, which is slope, and then we'll basically get the equation of that particular line. Can we do the same thing for, let's say, now I want to answer. I want you guys to answer. If you can quickly do that, good. If not, if you've got calculator, you can do it in like 1 second. What will be the price of, actually it's written here, so anyway, the price at 300,000 feet square will be $470K. So anything which is lying on this particular line, we can basically predict that price, right? So we'll basically take that point and we'll predict. But you see that these x's are basically the actual data points reported by a company or reported by some real estate, right? Okay. So so y is always the dependent variable, and we've got independent variable. So what we just looked at, you saw that these x's are data points. Now there's some gap, there's some distance between this point, these x's, and the line. Now that gap is the error. The line can never, it's a linear line, right? It's a straight line that needs to fit. So it's never able to fit all these data points, and it shouldn't either. That's called overfitting, if it fits the entire thing properly. So we'll talk about it later. But if you guys want to take a screenshot, whatever you guys want to do, please feel free. So training example, error, loss. I'm going to write down something from here. So don't mind, I'm going to copy this because this is going to be important. It's a cost function, okay? So we're going to do something with the cost function. I'll talk about what the cost function is. So it's j of theta 0, theta 1 by 2m summation of xi by yi. Okay, so basically this means prediction versus the actual observed value. Oh, it's here. Let's look here again. So if you guys don't understand it, I'll go again one by one. H of x, yes, loss function is different. Loss function is very important. That's what we're gonna, sorry, loss function and cost function, right? Both are the same thing. We want to minimize the cost, we want to minimize the loss. That's what we're gonna do. Loss function, cost function, it's called both. That's what we're gonna do. So is everyone following me right now? We're trying to fit a straight line through all these data points, but there's errors. These red dots are errors. This yellow line that you see is the hypothesis function. That's why I call h of x is y equal to mx plus c. You can write it like h of x is equal to theta 0 plus theta 1x, right? The error or loss is basically h of x minus y of I. You can see this particular line here, right? Why? Because this entire thing is h of x minus y of I. So that's why this is a cost function. And y2, 2 by m is basically the training number of data samples or training data samples, okay? Cool. So I hope you guys have followed till here because we're going to derive something very nice. So we're going a little deeper into the math of it. Why is the cost function important? And we want to minimize this cost function. We want to make sure that the error is as less as possible. Okay, so it will take a lot of time to do this entire math. So I've taken screenshots. So you guys, I'll explain it to you guys. Okay, so basically I've taken 3 different points, x1, x2, x3, and these points I'm going to calculate the cost of that particular point, right? So I'm going to do this entire formula and that will give me some points. What is x1, x2, x3, these points? x1, y1 is 1, 1. So if you guys want, I can write it down. Should I write it down or are you able to understand it? So we're taking 3 points, 1, 1, 2, 2, and 3, 3. Okay? Because this is important. If you guys have to understand how to minimize a cost function, you need to understand what we are doing here. Can I get some replies? Should I write it down or is it okay? Because basically what we're doing is here we have just taken one variable. So this was a cost function and we have completely ignored. Okay, fine, I'll write it down. No worries, no worries. It happens. Okay. Even I am learning, so it's okay. H of ix. So this is the h of x, or it's called the hypothesis function, right? So what if we just completely ignore this for now and let's focus on theta 1. So that's what we're doing. So instead of theta 0, we're not focusing on this. We just want to minimize j of theta 1. Okay. I hope this is okay. Whoever said. Okay. Theta 1. So if we just write theta 1, this is the value that we get. So we don't have theta 0. We are going to nullify this and we'll only get theta 1 x1 minus y1. So that's what you get, okay, for m equal to 3. So we're going to put these points and we're going to find out the value. So when we find out the value, you can see on the left, it's the hypothesis function. theta 0 plus theta 1x. That's the hypothesis function. And on the right, you can see the cost function. Why am I deriving the cost function? Is just to show you guys how the cost function will look like. Okay, that's it. Don't worry about it. If you don't understand it, it's okay. If we put theta 1 equal to 1, so you'll basically put 3 training sample, like m equal to 3 because we've taken 3 samples. So j1 will become 1 by 2m, and then we've got 1 comma 1, and these 3 points are there. So 1 comma 1, 2 comma 2, 3 comma 3, and we get j1 equal to 0. So we've got this point 1 comma 0 on the right hand side for j of theta 1. Okay, so similarly we'll calculate cost for 0.5, and if we continue to do this, this is what we derive at. Okay, now guys, try to understand what I'm doing here. We're trying to derive, we just derived the cost function for that particular hypothesis function. What was our hypothesis function? Y equal to mx plus c, or h of x is basically theta 0 plus theta 1 plus x. Now this is a cost function. So if you try with other values of theta 1, you'll get to see this bowl shaped curve, and this is what we want to minimize. I hope this is a very nice intuitive understanding. You guys are able to understand this, right? Because we are going towards something called as gradient descent. This is my favorite topic, and that's why I put a star on top of that. What are we doing here? We're trying. So let's take a beautiful example to, understand gradient descent a bit more. So I'm thinking, what should we do? So please take the screenshot. So this is the particular formula for gradient descent. I'll explain how we arrive to that formula. What are we doing here? So we basically initialize a random weight, which is basically we pick a point which is x equal to something. We pick that point and we define a learning rate. Now I couldn't have understood that. Is it better now? Yeah, there's some problem with the microphone, but I have my. Is it better now? Can someone tell me? Audio back again. Thank you. So gradient descent. We initialize some weight, and then we have some learning rate. So based on that learning rate, we'll find out the new weight. So what is it? Weight new equal to weight old minus alpha. Alpha is learning rate. If you don't understand this, I'll explain in a bit. Star d of, what is it? What's the variable used here? D of w, right? D of j and d of w. D of j is the cost function. Okay, so let's try to understand gradient descent a little more with an example. Let's take a simple example of x square minus, this is a quadratic function. What is f of x, guys? Quickly. You need to do this very quickly, right? So we're trying to, so we'll do this gradient descent for both the slope and the both the coefficient theta 0 and theta 1. We'll come to that later. We'll just trying to understand what batch gradient descent is, or just called gradient descent. Okay. Is anyone here trying, like, finding this very difficult and be like, oh my god, this is not the math I came for? I hope everyone's trying to follow. Okay. Because I took a lot of effort into, building all these things, learning all these things for you guys. So please stick around, and I will try to make sure that, okay. I'm not the best at drawings, but I guess you get the, okay. Someone's saying I can go a little slower. Yeah, I just want to see how it all connects. Thank you, Neha. Okay, bit fast. Pace is fine, right? Because we need to cover so many other things, right? Okay, so this is a quadratic function. Looks very beautiful, nice curve. X square minus 4x plus 3. And f of x is 2x minus 4. So basically, we can take a point here. And we can try to put alpha equal to, let's say, 0.1 or whatever. Put 0.2. And it will try to, find a new weight here. It will keep going here, 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 here. So this is called gradient descent. And slowly it will reach this point. This is called the global minima. What is this point? This is where x is equal to 2. Put x equal to 2 here. Fx, x equal to 2. So it will become 4 minus 8 plus 3. Right? F of x is minus 1. So this is minus 1. Makes sense? We have found, and I will do this in code. Neha, you said, how do you do all of this in code? I will do this in code. I will, once we are back in the computer again, I'll show this exact same thing with code. Okay? Yeah, I'll speak about that, Neha. We can connect on that later. Yes, I'm learning this for myself as well because this is really important. You are going to be the builder of AI. You need to understand how gradient descent works. Otherwise, no one's going to have credibility on your work. Okay, so this is global minima for fx equal to x square minus 3x. So I'll explain how this thing works, how I've changed, how I've used the learning rate equal to 0.1. I'll explain how I've used it, right? Let me go back to the slides again. This is gradient descent. So we initialize a weight and there's a learning rate as well. The new weight is basically w new equal to wl minus alpha. This is the minimum point of the cost function. I've taken a very easy example to understand. So let's the challenge here. So let's take a approach. Let's try to understand it even further. Because after this, we'll also go to the code. Wow, that's a huge compliment. Himanshu is saying that you taught me math better than Andrew NG. He is literally the god of AI. I respect him quite a lot. But thank you so much for appreciating Himanshu. This is just my first class. I'm also a bit nervous, but let's keep going. Okay. So we are trying to minimize a cost function. Let's play a game. A bowl-shaped curve is an imaginary hill, blah, blah, blah. Let's not look at the story here. Let's try to understand the math behind it. So we basically, how far can you jump each time in given this algorithm? So there's a frog. He's starting from θ1 equal to 2.5. So he has to arrive at this point 1, right? So he will move down with some learning rate. So new position is basically θ1. Update new position, previous position. So basically every time the learning rate goes, so he will keep moving down. Okay, so we're using the derivative of a cost function. Now I can take a learning rate based on my understanding, but there's something that you guys need to understand is if we take a very high learning rate, this is what happens. Okay, so it will completely bounce from global minima. So game over. So he has to try again. So we cannot take a very high learning rate. This is something that I took a lot of time to understand. Why can't we take high learning rate? And this explains why we cannot take very high learning rate. What is the learning rate here? Alpha equal to 1, right? Now it's taking alpha equal to 0.1 in the first iteration. So if I keep going into the math, if I do this derivation, it will take a lot of time, but I can show you how this one works, right? So we started from 2.5 and alpha equal to 0.1. We keep going down, and on the 20th iteration, theta 1 equal to 1. So basically we've reached the global minima. So this is we minimize the cost, or j of theta. So we know j of theta 1 is this much, right? So that's it, we win. We've taken the correct learning rate, and this is very important. If you guys have understood what I've taught you till now, take a screenshot and don't ask me why, because this is very important for a lot of people to understand gradient descent. Number of iterations. So you define an initial weight and you start from there. So you can take a random weight based on your understanding of where the global minima can go. So number of iteration can be 20. Initial theta 2.5. So we have taken learning rate equal to 0.1. 0.1 is good because it converges nicely in 20 iterations. Okay. And the next one, number of iterations is 20. And initial theta is 2.5. Learning rate is too low, so it doesn't reach the minimum. And the third one, number of iteration is 100, and we have taken initial theta as minus 0.5. Learning rate is again too low, and it takes a lot of time, but it converges. Okay, so it really depends on where you take that initial theta 1 or that initial weight from. Okay, old weight. So I hope you guys are still with me. I hope people haven't dropped off, because this is where we are going to go for a little bit of NumPy and Pandas tutorial. Let me see. Yes, 45 people are still here. Thank you. And let's go back to code again. Thank you guys for sticking around. I hope you had a nice time understanding cost function. And I will go back and, summarize what linear regression is. Do you guys want me to summarize linear regression for you guys right now, or do you want to see the code first for linear regression and gradient descent? All these code are up next. Okay, at the end. Let's summarize linear regression at the end. Okay. So how's everyone doing? I hope all good so far. Let's go to the NumPy tutorial. This is for people code first. A lot of people are, yeah, let's go back to code again. Okay, so let's go and share some code. So where did we end up? Yep, NumPy and Pandas tutorial. Yes. So how many people, just drop a message on the group, that how many people have never done Python at all? Yes, recording zarur milegi, don't worry. If I don't give recording of this one, people will be like, oh my god, so you need to give me recording for this class. There's so much of math, there's so much of code. But gradient descent, I think you guys understood why we're doing gradient descent, right? We want to minimize the cost function, and I'll also show you the code for gradient descent. So learning Python now, can we get code? Of course you'll get code. So I will make sure all the code that I'm showing here, I will put it on a GitHub repository, or even everything will be there on my Notion site. So I'm making that site to make sure that every learner, whoever's doing this class, can go back to that site and then can refer back to these videos and also the code. Let's quickly start. What is NumPy? If someone can define NumPy in the chat, if you guys are an expert, go ahead, do that, help others, please. I'm going to continue this. NumPy is a library in Python that we use for mathematical operations, for creating arrays, working with matrices. It's a super useful library. You must know NumPy if you want to do AI, computer vision, because NumPy arrays are extremely fast. And when you're working with tensors, you will see NumPy array a lot. So basically, when you work with one-dimensional array, it's still okay, two-dimensional, okay, three-dimensional. But when you're working with n-dimensional arrays, that's when you need NumPy, okay? So this makes mathematics way easier than if we didn't have NumPy. I don't know what we'd be doing. There'll be a lot of code for that. So let's define, this is a NumPy array. I'm quickly going to go over all the, you know, small snippets here. So you import the function NumPy, you import the library NumPy as NP. This is standard practice. And then you define an array, np.array 1, 2, 3, 4, 5, and I'm just printing out the array. Similarly, I'm showing you all the functions that we can use. 0. So this will define a 3x3 matrix of all zeros. Then 1, I'm defining a 2x4 matrix. So there's 2 rows and 4 columns of ones. np.full, we can basically have, we can define the number here and it will basically give you a square matrix, 2 by 2, 3 by 3, whatever you want. How many of you remember identity matrix? Been a long time since I did it in school and then in college sometimes, I guess. Yeah, identity matrix. So you'll use np.I. If you put 4, 5, whatever you want to put, you can get the entire matrix here. Okay, this is something that you're going to use a lot. np.arange. So 10 is not inclusive. So we basically putting numbers like 0 to 10, but at an interval of 2. So we've got 0, 2, 4, 6, 8. Linspace or linear space is very important as well. We use this. I'll show you how I've used it in creating synthetic data, or you can define some numbers. So basically between 0 and 1, if I want equally spaced points, 5 intervals, then I'll use linspace. If I give it 4, let's do some modification here. Let's see. So this is 4. What about 10? You guys know what the answer is going to be, right? Cool. So this is linear space. All right, this is reshaped, and slowly I'll go over. So we define 2, and then we can do basic operations as well on NumPy array. We've got add, subtract, multiply, divide. These are element wise operations. So basically if I add 2 arrays, if I subtract 2 arrays, multiply, and if you've done matrix multiplication, you know how this would work, right? So np.dot product, it's a very important one. This is the dot product of these particular arrays, right? Then we've got some statistical operations as well. We've got the mean, we've got median, standard deviation, and we can use directly these functions. So it makes life easier. That's about it. Yeah, we can do slicing, and these we already know. I think people who have done Python or whoever's learning Python, right? They know slicing already. So we can define conditions, and this is the important one. We can use np.where. So basically it will, so the condition is a greater than 2. So it will find np.where a is greater than 2. Following till now? Yes. Best thing is if you practice code using pen and paper, and that will give you a lot of confidence in writing code in the interviews if you guys are preparing for jobs and stuff, right? If you guys are preparing for job, then you must know all these things. This is very important. No one's going to ask you MLOps. No one's going to ask you how do you deploy a machine learning algorithm in production, like for MLE2 maybe, but not for MLE1. Okay, so moving on, got the random function. We'll be using random function a lot as well. So we get a 2 by 2 matrix of random numbers. We get a 2 by 2 matrix of random numbers, and this is basically for float. Now we can define integers as well. So yeah, we'll define what integers we want. So we'll define that 0 to 10, we'll get all the integers, and this is going to be a 2x3 matrix, so we can define the size as well. I hope people are following till now. I'm not going to go too much into that, but I'm just showing you the basic functions, and np.sum, np.prod, okay, cumulative sum, and yeah, that's about it. These are all the other functions like concatenation, virtual stacking, horizontal stacking, and yeah, this is the entire array, so we can stack it. This is a very useful one when we use we'll use NumPy a lot. Okay, if you want to implement algorithms without using the libraries directly, so you'll need to use NumPy a lot. So master this stack. That's why I just chose NumPy and Pandas to revise, or people who don't know, people who are just learning Python. So I wanted to. What does this code do? Like, this is just a starter code. This is not doing anything. This is just showing you what you can do with A and B. Like, this is just showing you all the functions of NumPy. Right? This is not, yeah. Basically, we're learning how to use the functions in NumPy. Okay, there's nothing. So basically, just playing with NumPy. Now we move on to Pandas. It's a very, very important library. I use it in my job. I've seen a lot of people using it in day to day. If you want to be a data analyst, if you want to be a data scientist, machine learning engineer, you'll be using Pandas a lot. Why do we use Pandas? In Pandas, we have Pandas series and Pandas data frames. So what is a data frame? Think of it like a table, but in a structured format. Now you can do many powerful transformations using Pandas data frame. So I'm creating a data frame here. So I'll define, this is a dictionary basically, and then I'll convert this data dictionary to data frame using pd.dataframe. This is a function in Pandas. So I've taken name, age, city. So these are just randomly 4 people, ages, and their location. And this is the data frame that I've defined. Even if you just write df, which is a common industry practice to use df for data frames. So we'll see that it's name, age, city, and we've got 4 rows. This is just a basic example because we're going to use Pandas as well in the next, whenever I show you linear regression, or even if you do anything, like if you're working with tabular data, most probably you'll just do quick analysis using Pandas. Okay. So basic data frame operation, df.head, df.tail, used it quite a few times. Head is basically you're viewing the top n. If it's 3, 5, you're basically viewing the top n number of rows. Let's say if I do 2, then I'll just see 2 rows. Same for tail, I just want to see the last one, so I can see that it's David. If I want to see the last 2, just do df.tail 2. Okay. Info, you'll see the info, the names of the column, the number of entries in those particular column. So this is a very important one. When you see that these numbers are not matching, you can just look at it at a glimpse and be like, oh, there's missing data here. So how do we handle missing data? This is also very important part of data science, where you know how to handle missing data for your analysis. Okay, so df.info, and I hope I'm not going too fast, right? I'm just trying to show you guys what these functions would do. df.describe, and then you can select particular columns and just leave out some of them. If you just want like name and age, or if you want just name and what was the other one? Salary. Let's say you just want to see the salary, so you would just write salary and you just see Alice salary, Bob salary, Charlie salary. Okay, cool. So ilog is basically if you want to see element wise what's the value. There's another called lock as well. So if anyone knows the difference between iloc and lock, please write it in the chat. I've sort of forgotten. It's a similar thing, I feel, but one is element wise, the other is index wise or something. .iloc and .lock. Okay, then we can do simple conditions inside the data frame. So basically, if you want to see age greater than 30, but if you want to see people greater than 20, there's a lot of people. If I want to see age 40, no one's there, right? So you see how powerful Pandas is. It's basically like you can slice your data, you can see different things, and this should be the number one thing when you open any new data set, open it with Pandas and run all sorts of EDA, exploratory data analysis, and then you go towards any machine learning algorithm. So you do a lot of visualization. You use matplotlib for that, and then you basically do some tests as well. Maybe you can do z-test. You do some statistical tests as well, or you have some hypothesis. So after all this, you can move to a machine learning algorithm if you feel that okay fits your. I'll also show a very nice notebook that I found for linear regression. It's a huge one. If I am to discuss it in this class, then we'll probably be sitting here till 12. So I'm just going to show you briefly, but yeah, let's finish the pandas thing quickly. So salary, I've just redefined the salaries here. So there's a lot of things basically you can do. You can drop the columns, and then basically I can, basically use to CSV to Excel to save all the data frames to CSV files. This is a very important one. And if I want to read from a CSV file, I would use something called as .read CSV. And in that, I can define a lot of parameters like what will be the separator, n rows equal to 5. So basically, if I want to, if the data set is too big, I just want to see the first 5 rows, or just want to see how the data looks, I'll probably just use n rows equal to 100, n rows equal to 10. So it's very powerful. And this was a brief introduction on NumPy and Panda. And I'm also going to show you what it would look like to work with a real data frame. Okay, this is what will probably interest Neha and some people who just saw like, whoa, we just learned like few functions, now show us the real thing, right? So you import NumPy, you import pandas. I'm just going to use pandas and not going to show a lot. I will drop the link here where you can go and find it, because this is more part of data science and we're learning machine learning algorithm here. So I probably might cover data science based on the interest. It's very rigorous. You try to understand how the data looks. It's definitely a part. Machine learning is a part of data science. Right? Data scientists do machine learning as well. So this is the data set. I've taken it from a GitHub account, and I'm directly loading it through a URL, and the read CSV function's been used. It's the churn rate of telecom operator client. Churn rate क्या होता है? Churn rate is basically whether that particular client is going to stay or not, right? So let's see what is the churn. Churn is going to be the y variable. Let's go back to no, burn rate is different. Churn rate is different. Okay, someone knows churn rate, just quickly write it down on the chat. Churn rate is basically whether the customer will stay or not. Churn rate false matlab customer chala gaya. Churn rate 1 matlab customer hai, or did I say it opposite? Churn 0 means customer is there, right? Churn 1 means yep. Okay, so I'm going to look at the data frame. I'm going to see what's the shape. So I can see that there are 3,300 rows, 20 columns. Is very important. That the first thing I do when I load. So I'll know that what am I trying to predict? I'm trying to predict churn. Now, what are all these things? These are all the features, or x1, x2, x3. This is called, if we put this into linear regression, what would this be called? Multiple linear regression. Okay, and there are a lot of things which we probably would or would not use, and a lot of times we see this kind of data, yeses and nos. I again told you that computer doesn't understand yeses and words, so we have to change yeses and nos to zeros and ones. And if it's a categorical value, then we have to change it to 0, 1, 2, things like that. Okay, so we always have to change it to numbers to make the computer understand. Okay, so I've like done some analysis of this. I'm not going too deep into it, so I'll use df.info to make sure that there's no missing data. So this is going to be an exercise for you guys, whoever's attending the class today, to yes, that's right, Anaconda, thank you. Churn 0 means customers there. Churn 1 means customers not there. What did I do? So I checked value counts of churn. So I saw that 483 people have left. So there must be something wrong, right? So let's try to find out what this 432 people are. So we'll try to, we can select if churn equal to true, then we'll see those particular rows and we'll try to form some sort of relationship between different variables, the independent variables to the dependent variable. Okay, now I've changed it to integer, so it will become 0 and 1. This is very important when you're predicting through linear regression or anything, because we need to make sure that all the data is in numerical format. Okay, so let's do a small example. What is the maximum length of international calls among loyal users? How do we get this? Just using pandas, right? We'll check if churn equal to 0, which is basically customers are there. So loyal customers, and international plan is no. So what is the total international minutes? Maximum, sorry. Yeah. What is the maximum length of the international call? So we'll find that, okay, so these are the people who don't have an international plan and they're loyal customers, and their total international minutes is 18.9. So that's why pandas is useful. So you can do a lot of data analysis through pandas. Okay, let's set up some plotting. Matplotlib, the classical library for data science, machine learning. Whenever you want to plot something, you can use Matplotlib. There are other libraries as well, like Seaborn, and you can use whatever you feel like, right? So I've used Seaborn here. It looks a little better than Matplotlib. So I can see that given the international, I wanted to see what is the relation between the international plan and the churn. So what I did is, like, I just plotted. So I saw that the people who don't have an international plan, their churn's 0. So basically they are the loyal ones. So people who have international plan, their churn is very high compared to the ones who don't have. So can I do a cross tab, which is basically check what's the numbers, whatever I just saw in the graph, I want to see the numbers. So we observe that churn rate is significantly higher with international plan. People who have international plan is pretty high compared to people who don't have international plan. This is noteworthy finding. So this is probably your assumption. Poorly managed expenses. This is what data scientists do. They look at data, they try to find the meaning from it, and they do the analysis. This is a big part of a job role of a data scientist, and data analysts would probably just make visualizations, right? This is what they would do. Data scientists would do a lot of tests like hypothesis testing, or they will create machine learning models, or probably try to understand the relationship between data. That's number one thing before you move on to any machine learning algorithm or even AI. Okay, that's knowing your data. So all good till now. Can we drop NumPy and Panda? All right, thank you. So let's go back. What's next? Gradient descent, right? I promised, what was the equation we used? X square minus 4x plus 3, right? This one. Oh, I see that there's some problem. Let me share that again. Okay. Yeah. Okay, now we're talking serious things. We're all good with NumPy and Pandas. Now we're trying to see how we can plot gradient descent with Python, right? So we import NumPy, we import Matplotlib, the classical plotting library. We define cost function. This is specifically for you, Neha, because you asked, can we do the math in Python or not, right? This was a question by Neha. So we define the cost function. This is basically a method like that will just return the cost function, which is x square minus 4x plus 3. What is the gradient? f dash f the differential of fx or f dash x, which is 2x minus 4. People who don't understand how we got this, go and study differentiation again. Okay. Learning rate, I've set learning rate 2.1. How many iterations? I'll change this and show you that what it means. Okay. I've set it to 85 because I was just playing around with the code a bit. So initial guess for x is like the starting point. I'm just saying let's start from 0, 0. And we're going to compute the gradient at that point. So what is the gradient? This is the value that's going to get. Gradient is that. I'm going to use x. Neha and everyone else, please try to understand this. Whoever did not understand the math, super simple to understand. Look at this. What are we using? Remember the gradient descent formula. W new or new weight equal to old weight minus learning rate into the gradient. Okay. So this is the formula that we use for gradient descent. The value of x after optimization represents the minimum of the cost function. That is true because x has now been minimized. So I'm going to save it in a variable called minimum x, and I'm going to save the cost function for that. So basically the cost function is this one. So I hope you guys know the difference between x and fx. Fx is the cost function, x is the variable here, okay, or the weight. Okay, x is, can you repeat this again? Sure, Yash, I'll go quickly. We are importing NumPy, we're importing NumPy for mathematical operations, we're importing matplotlib for plotting. This is the cost function which I've defined. If you remember in an example, we were trying to do gradient descent on x square minus 4x plus 3. Now that's a quadratic function. If you plot that, you will see a bell curve. Okay, we are trying to find the minimum of that particular cost function. So we want to understand at what x is my cost function the minimum. So I'll define the gradient. The gradient is nothing but the partial differentiation of fx. So it will be 2x minus 4. I've defined learning rate alpha. This can be changed. This is a hyperparameter. I can change it and get different values. I've set iteration to 85. I'll change and show how the results look like. And the minimum of x is 1.999999. So you see this is converging. What is the minimum cost? Minus 1. If you remember the chart, if you don't remember, I will show it to you on the camera because I'm not going to move to my iPad again. See this. Okay, if you remember the chart, this was the bell curve. Okay, sorry, not the bell curve, my bad. This is not the bell curve, this is a bowl shaped curve. Bell curve is different. So it looked like this, and the minimum cost was minus 1, which is f of x, and value of x was almost 2, right? Let's change this. Can we get it in 10 iterations? Probably not. You see that I have not reached my minimal cost yet. Let's see if I change the initial path to 1. Can I reach now? Nope. So it depends really, right? So these are hyperparameters. This is the beauty of machine learning, guys. There are so many hyperparameters that you can tune to make your algorithm, to make your gradient descent algorithm interesting. So work on this, try to understand how you can tune these hyperparameters. The initial point, number of iteration, learning rate. I can change all of this and I can get different values, right? So for now I can just do, now you might ask, okay, sorry, how are we trying to understand, like, see, how are we converging it? So I've done the same thing again. This time I've set the maximum iteration to 100. I'm telling my function that, hey, you know what, if I converge, then don't run after that. So let's see. Iteration 0, iteration 9, 10, 20, 30. I just wanted to check what's the status in different iteration. And I can see what's the starting point here. That's very important, right? Oh, it's a random one. Okay, so I'm randomly choosing one, and basically this is the point that was used, and I reach x equal to 1.9999 or close to 2, and the cost is -1. Plot it, and you can see that the cost is reducing significantly as we increase the number of iteration. Looks good, guys. Code's interesting. Let's plot gradient descent now. So I was trying to plot gradient descent, and I was trying to make the frog jump, use the dots and everything. And this is the beauty of code. You can plot all the mathematical things. What have I used here? I've basically just used matplotlib and NumPy, right? So I'm not using anything else, and we can just directly get all these values. I can put it into gradient descent, and I can plot a very nice, neat looking gradient descent iteration on fx. Looks good. Can I have some cheer on the chat if it looks good? And you guys have understood till now, so I know that I'm not speaking to a blank screen. Perfect. That's the entire point of doing live classes, right? I know some of you might be finding it so hard and be like, huh, this guy was probably just talking weird random things in the last class, and look at him now. Right? Because I didn't want to overwhelm a lot of non-technical people. That's why I told them that this is going to be a non-technical one and this is going to be a technical one, right? So we are done with gradient descent. Let's move on. Let me stop and let's move on to the next topic. What is the next topic? Linear regression code. So let me share my screen. Everything looks good. Now we're going to do linear regression in the code, right? One thing that I probably overestimated was how much I can probably teach in 2 hours. And I realized I probably took a lot of it. I don't know how much I can put. I'm just like at half of my slides, and we still have to do decision trees, logistic regression, and also have to conclude. So let me know if you guys would be interested for a part 2 of this, and we'll go even deeper into the math and the code, because you can spend endless number of hours with linear regression. Yeah, right? Part 2. Perfect. Definitely, for sure, I'll do that. Okay, let's look at real things now. We're talking linear regression. For the beginners, I gave you some time to understand NumPy, Pandas, and we're going to use a library called sklearn or scikit-learn. So very useful one, very simple one to find machine learning models, and we're going to use train test split. Okay, now I think I forgot to tell you about train test split, but just understand that we have the entire data set. This is 100. I'm keeping 70 or 80% of it for training data, and the rest 20% or 30% for testing. Why? Because if I show all of my data to my machine learning model, what am I testing on, right? It always has to be tested on unseen data. I cannot tell, hey, I've got this amazing machine learning model and I'm testing it on the same data that it was trained on, right? So we need a train test split. What are we importing from the next one? We are importing linear model, which is linear regression. Let's keep going. So anyone who knows about np.random seed 42, why do we use 42 and what it does, please write down in the chat. I will give this to the people who are enthusiastic and they'll take it up to explain it to you guys. Okay. So I'm basically taking very random, sizes, and what we just did, right? I wanted to use the same example for the square feet, the size of a flat versus the price, but I couldn't find like something easy. So I created some random numbers between 1500 to 2500. I hope that's fine. This is synthetic data. Okay. And I'm also like creating the prices also like very randomly. I'm just multiplying it by 200 and then adding a random number, right? So I've defined the slope as 200. I've basically done a linear regression already. I have defined some random noise with linear relationship. Why did I do that? To make sure that the final plotting looks good. Okay, otherwise it doesn't look good. You'll be like, whoa, what did I just learn? Doesn't make any sense. Okay, quickly, we created a data frame, sizes and prices. What are we doing? We are predicting. What are we predicting? Price. Price is dependent variable. X is independent variable. How many x's can be there? Depending on how many dates you've gone to. Basically, x1, x2, x3 depends. You can have multiple features, but here we just have one feature. We've got size and price. What we're doing here, this is a very important one, and you'll see it almost in every machine learning same way: train, test, y train, test. Why? Because x is basically, I'm splitting the training data into y train x test and x train. So I'm taking, what is my train test split? 80% I'm keeping for training, and 0.2, which means I'm using 0.2 or 20% of my data for testing. So I'm splitting out. So x test and y test are both labels which my machine learning model doesn't know. Why do I have y test? That's my answers. Y test is my ground truth. I'm going to use y test as the observed value, and y pred or predicted value will be my numbers which my machine learning model has given. Okay, so initializing the linear regression model.fit. This is where the real action happens. I'm fitting a model on the training data. I am giving it the data, which is x train, and I am also showing it the label. That's why supervised learning. Let's make predictions. Y pred, that's what I was talking about. It's predicted on x. It's a very easy code for you guys to understand, because I know that there's a lot of beginners, and this is also going to be a prerequisite for people who join the next classes, right? So I don't have to go through this again. So y pred is basically the predictions, and we'll get that from x test, right? We cannot use x train here because that will give a different size of array. It will give the 70% of data. So make sure you're using the x test. And then I'm plotting the data points. I'm plotting the regression line and the intercept and the coefficient. That's it. And I'm using something called as root mean square error and R2 score. It's a very important one to evaluate how my model has done. Looks good, guys. A lot of people have like suddenly found interest because like, yay, you know, math code. Looks good. This is my line. This is my actual data, which is the blue points. The only reason I used NumPy or the random data is because it just looks good. I found this nice. So the regression line that you see here. So if I give you these values, can you basically tell me the price of, let's say, price of an apartment which is 2,300 square feet? So I'll do this and I'll check what it is here. We've got the numbers, we've got the coefficient, which is basically the slope, we've got the intercept, and how well has our model done? It's got 0.83. So R2 score can range from 0 to 1. Anything above 0.7 is a good one. RMSE is 28,000. Basically, what 28,000 basically means, it's the root mean squared errors. What does this mean? So you see these blue dots. If you dot this to the line, this is error. So if I do this for all the points and I take the mean of that and I square the errors, that will become RMSE. So it's telling me that because the prices are in like 100,000s, right? So it will tell me that, you know what, if my machine predicts, ML model predicts something, a price, it will predict something in the range of plus minus 28,000. If I said that right, okay. But if I said something wrong here, please feel free to correct me in the chat. So RMSE is basically telling me what the root mean squared errors of all these lines together, all these data points together, have found out, like for this particular use case. So are you guys happy with this linear regression model? Can I have some replies, please? Perfect. Thank you. All right. Okay. So I'll be sharing all this code, but I know you guys are happy with this linear regression code, but I'm not. So I'm going to give you something more better. And this is a good code, or this is the actual data science code that you probably should be aiming for. And if I start doing this, I don't know how many lines of code this is, but it's a big one. The size of this IPython notebook is around 2.2 MB or something. And this is a project. This is a housing price prediction project with real values and stuff. Okay. So we'll try to, so there's a lot of libraries that's been imported. And if you see the data set, this is the actual data set, looks much better. We've got lots of features. We can build a proper multiple linear regression model on this. And that will be a nice regression problem to solve. What is the target? The target is price. Where is the price? Price is here. And what are the features? The features is all these things. So we'll select, we'll do feature engineering. We'll look at the relationship between the features and the y, or the target variable. Okay. So we'll do lots and lots of data science here. We'll do EDA, right? We'll first see what's the median value of homes are. Okay. Is it normally distributed? And then we'll visualize on categorical features, and we'll see, okay, what is it? Do we have any data imbalance here? Then we'll look at numeric features distribution. Then we'll do a pair plot. Okay, it's a very cute one between all the features. So we'll try to understand, is there any sort of multicollinearity between the data or not. I don't want to overwhelm you guys, but just showing you that this is neatly written code, a proper small machine learning project using regression and all the other things as well. There's a lot of other things used as well. So we do some data pre-processing, which basically means we want to make sure that the data is all good for machine learning model. So in most of the cases, guys, you will not find good data. Okay. And yeah, we'll talk about careers at the end. Okay. I will probably like make a part 2 of this because we've already crossed like 8 p.m. and I want to, go in depth with decision trees, and there's so many things. Like, it's just very interesting to talk about the math and the code. So I can keep talking about this for hours, but I've got a hard stop at 8:40 or 8:45, and then we have another class for someone else. Okay, so this doesn't have any duplicates, and basically we are checking the data. It's a lot of dummy encoding. We check the features, or we are looking at the final data set. It's a very nice visualization. We saw that, okay, 2.2% of the data set has been dropped, and the rest 97.8% has been retained, because this was probably like dirty data, which is the outliers and everything, which will probably make our machine learning model really bad. So we do these sort of things. Then we do data manipulation. Basically, this entire data set only has 545 samples. That's a very small data set. We need thousands and thousands of lines to make a good machine learning model. Machine learning model needs data to learn from, right? So we have the training set, which is only 426 samples, right? And testing on 100 samples. So we'll do all these things, standardization on training set. You guys feel free to, once I upload this, feel free to go through this. Okay. Feature selection, we'll select all the features which are highly correlated, and whichever is like looking good with the price. You'll see the bedrooms and stuff, like these are highly negatively correlated, or the red ones are positively correlated. It's a heat map. Testing a linear regression model with stats model, we're testing it now. These are the important, so anyone from statistics background, you must be knowing all these things, right? It's a little bit of statistic and we do all these things. Okay, so a little bit of statistics here, manual methods. There's a lot of things, training RMSE, testing RMSE, just to see if you're not overfitting on training data. Okay, so then we do a lot of things. This is a little advanced PCA, principal component analysis, which is under unsupervised learning, and or probably taken the data class. It's a little complex for now. Train RMSE, test RMSE. Just look at this. It's a very nicely made Jupyter notebook. Predictive modeling, multiple linear regression. This is what we learned, right? Y is the dependent variable, beta naught is the intercept, and then we've got all the slopes for x1, x2, x3. Then we fit the model on linear regression. We standardize the x and everything. So this is the actual and this is the prediction. So it looks good, probably not that good. So we have to understand, and we need to do inference, and we need to understand the evaluation metrics. Okay, so a lot of things. Lasso and range regression. These are when you add penalty called L1 and L2, right? So this is a little advanced, elastic net. So there are different type of regression. You can feel free to read up. There's something called a spline regression as well, which is very good in nonlinear cases as well. Polynomial regression model. This is a good one, and this performs the best. So you see that this guy's done a lot of work. I found this Jupyter notebook from Kaggle. By when I will send all of this by tonight. I'll probably upload it in a GitHub repo, and I will update that repo into my Notion site. Is that good? Yeah, cool. So we're comparing the evaluation metrics, and we see that polynomial regression does the best out of all the other ones for R2 score, which is good. Now you'll have to understand why it does well and stuff like that. These are all the regression models. So the best thing to do is to test all these models, all these regressions before you can choose one. So there's different type of regression, right? I just touched upon linear regression, and he's tried all of this, and he's gone with polynomial regression. Anyway, so I hope you liked it. This was something I liked, so I thought that why not show a real world use case, and you can use the same sort of code in different data sets from Kaggle, and the goal of this is to learn, right? So anyway, I will close it now. I've also done linear regression, NumPy is done, Pandas done. There's one more thing which I wanted to show you guys. This is called a Colab notebook, which basically means that I don't have to download Jupyter notebook. How do you download Jupyter notebook? You can just go to Google and search download Jupyter, but I prefer downloading it through Anaconda distribution. So if you download Anaconda, you will get all the I think you'll get all of this. You'll get all the data science libraries you can find, PyTorch, TensorFlow, all these things will be there. So you just need to like do conda install PyTorch, conda install TensorFlow. If you've got an NVIDIA GPU, you can also use CUDA, and basically all these things are there. So it is made for machine learning and AI. So just go ahead, download Anaconda, and you can use Jupyter. It's also open source, so good. And Colab is, anyone who knows Colab, please feel free to comment in the chat, Sahil or whoever knows Colab. Okay, so you can install libraries like pip install word cloud. I'll show you this word cloud at the end of the class, which is basically the response of the Google form that you guys gave. Because if you're not playing with real world data, then what are you guys doing, right? So this is all the response that you guys gave on the Google form. Not going to show exactly what it was, but I created a word cloud using it. The bigger the word, yes, Google Colab, yeah. The bigger the word, the more number of occurrences it had in that particular question. When I asked, what would you guys like to learn in the next class? So a lot of you said AI, ML, learning. I think it was probably from deep learning or machine learning, NLP, LLMs, and there's a lot of things. So the smaller the word, the less it's been used. Algorithm. So yeah, okay. So yeah, I've used it for different things. You can use it, you can directly, but the only problem is like after 90 minutes, it gets disconnected because it's online. So yeah, it's very good. If you pay for it, then you can use GPUs as well, TPUs as well, which are way more powerful than our GPUs. And what we can, if you're training big machine learning models, then you can use Google Colab. Okay, so let me close it for now. And there's nothing interesting in this one. I decided to go with good old Jupyter notebooks to show you guys, just in case if I couldn't run it after 90 minutes. So yeah, but I'll anyway post the Google Colab link as well. So we did linear regression, and are you guys able to see it? Not sure, like, you guys able to see the presentation? Okay, cool. Let's continue. So the main assumptions for linear regression is basically the relationship between the predictors and the outcome is linear. Okay, so one of the most important ones, and there needs to be independence, which basically means the observations are independent of each other. So if I've got x1, x2, x3, x4, xn, then I need to make sure that these are not correlated. That's why the guy who was doing that, he did something called as multilinearity, which is basically checking whether all the x's, x1, x2, x3, are they correlated or not. So these are some assumptions, or these are some checks which you should do in the and then there's other things as well. So if you go and just Google it, what to take care of, what to do before making sure that we can apply linear regression to the data or not, you will find out these things, that the errors of the model are normally distributed. Okay, so let's summarize. Are you guys ready for a summary for linear regression? I hope at least we make sure that we spent like 1.5 hours on understanding linear regression at least, and gradient descent. At least this should be completely clear in everyone's head. So we've got the slope, intercept, estimator of error, observed value. Really nice graphic. It takes a lot of time to find these nice graphics and put it, for people to intuitively understand. We also went through the equation of a straight line, which is beta 0 plus beta 1x, which is y equal to mx plus c. And if you add the error, basically, the error will be added to the linear regression equation. Okay, really nice graphic. Take a screenshot. You should never forget linear regression. Okay, if you attended my class, you should at least know what linear regression is. Or what if we have more than one independent variable, x1, x2, x3? We've already talked about it. There's only one dependent variable. We're predicting y. Avengers get together, x1, x2, x3, all of them. Let's predict y. Let's make it better. So the more number of independent variables or predictors, the better. Can you scroll back one slide? Yeah, sure. Can you take the screenshot quickly so I can move? Okay, and you can also find the recording, right? So what if you've got more than one independent? So it makes the model much better. We have got MLR, multiple linear regression. Okay, take a screenshot if you want quickly, and you'll also find it in YouTube. Strong positive relationship, strong negative relationship, no relationship. If the data is distributed, like what is the like? There's no relationship between pet owners and percentage of college educated, right? So that's why you'll find like random distribution of data. So that's mostly the case for real world data, right? So it becomes very hard for you to fit a linear line into such data. So there's a lot of memes, and I don't know why this is. Sorry about that. Yeah, I think there was some problem with Canvas. Yeah. So one of the problems that I want to talk about is non-representative training data. I'll make it very, very simple for you guys. See the red dots? So basically what we're predicting is the life satisfaction and GDP per capita. The question that we're probably asking ourselves is like, is the life satisfaction better where there's more GDP, right? So if we use the blue, only just the blue ones, right? If we use this one, the blue ones, then we see this dotted line. This is the linear regression line that we can fit on this data. But we've got, these are real life values by the way, but we've got these outliers like Brazil, Mexico, Luxembourg, Switzerland. And if we use these data points, then our entire linear regression line shifts to fit these two lines as well, right? Because of the outlier. So if you have non-representative training data or outliers in the data set, this will make your entire model wrong. Okay, because I can't really say that if there's a country which makes a lot of money, like high GDP, they are not better off than countries which make less GDP. Can I make that call based on my linear regression model? No, right? Because the training data is non-representative. So let's talk about underfitting, good fit, and overfitting. Overfitting is basically, you see this, these are like the training data, and my model is literally learning the patterns of training data. Now, if there is a test data and it will perform really poorly, this is an overfit model. Same for underfitting, and this is not good either. It's not able to predict a lot of values. So this is called underfitting, and this is a good fit, right? But this is not necessarily a linear regression model. Okay. This meme was going viral, so I thought, why not use it? So we have learned linear regression. So when you see any data set, if you want to try with linear regression, go ahead. It's very powerful. You don't have to use deep learning or LLMs or XGBoost, which is a type of gradient boosting. So you can use linear regression. By the way, this guy on the right, he won the silver medal from Turkey. He's probably 51 years old and terrific. Okay, so logistic regression. Despite its name, it's used for classification. So we talked about a regression problem, right? So we will now look at classification, but you might be thinking, but it's logistic regression, right? Why are you using it for classification? Because it predicts the probability of a binary outcome. What will be the outcome? It will be a binary outcome, 0 or 1, yes or no. There can be multiple type of logistic regressions, but we'll come to that in a bit. But we are calculating the probability of a binary outcome. We are not calculating continuous variable, right? Which can be used to classify observation. So let's predict a categorical variable. So logistic regression can be classified into three types. Binomial, which is basically two outcomes, 0, 1, pass, fail, hot, cold, etc. Multinomial, which is basically we've got more than two categories, cat, dog, sheep, Audi, BMW, Mercedes, things like that. Ordinal, which is when we have some type of dependency, like there's an order. Ordinal means there's an order, low, medium, high, etc. 1, 2, 3, or something like that, right? Okay, it's time for math again. I see that this class is extending quite a lot, and I will try to sum it up to probably, and we can like take up decision trees in the next class as well, because there's a lot of content for decision trees, and we'll have to understand random forest and all this as well. But yeah, let's try to complete logistic regression at least. Okay, cool. Let's start with the math here. Share my screen. Okay, can you guys see my screen? We have moved on to logistic regression now. What are we doing? Yeah. Okay. So let me quickly derive the logistic function here. And we'll also try to see what a sigma. So this is okay. Hope you can hear me again. There's probably a box coming here. Okay. So we're talking about. Can you hear me now? It's a background noise. Please reply on the chat. It's only 29 people, I guess. Can you please reply on the chat here if you can hear me? It's fine. Okay. Thank you. So we're doing logistic regression. So the first thing that you should know is it's used for classification. Okay. What are we doing? We're predicting probabilities. Okay. Of the outcome. So I'll go a little bit towards this. So beta naught is the coefficient, or basically the intercept, and beta 1 is the slope. But we want to predict the probability, right? So we'll take the probability. Let's say P is the probability of that outcome, right? But we don't want to predict the probability, because here it might exceed 1, or it might go below 0. Okay, so we don't want to use the probability. So what we'll do is we'll use the odds of P. Now if someone can tell me what's the formula of odds of P, I'll use that. This derivation was not there, so I thought that I'll give it to you guys so that you can understand how it came from. So odds of P is basically the chances of success versus the chances of failure of the event P. What is it? It's P by 1 minus P. So if I put this here, P by 1 minus P, so I'm using odds of P. I'm not using P because it can exceed 1 or it can go below 0 as well. So this is equal to beta naught, beta x. Okay. And but there's a problem here as well, because this particular thing is probably between 0 and infinity, but we want something between minus infinity to infinity. So what are we going to do? We're going to use the log function. So we're using log of P 1 minus P equal to beta naught plus beta x. So let's take this forward. What did we have? Log of P 1 minus P beta naught plus beta x. So let's let's derive the logistic function, and then I'll show you what it looks like and why it's very important. We'll also understand sigmoid. So that's an activation function. I'll talk about it in a bit. Okay. Right. So we've got log of P by 1 minus P. So we can take the exponent on both sides. So if I do exponent of log, just trying to derive it, guys, so that you understand that how this thing came into being. Okay, so this is basically like e to the power ln, which is natural logarithm, right? This is e to the power beta, right? Okay, so now this will get cancelled because it's natural logarithm, so it will come like 1 minus p e to the power. So back in school we used to our teachers used to deduct some marks for skipping steps. I'm going to skip steps and I'm going to directly go into the last one. So if you do the math here, basically you move the p here and you multiply it with e to the power this and that. So you will get to this result. Okay. I'm skipping the math here. Please feel free to do the derivation. A lot of people might find it very difficult. This is the logistic function. Okay. Now this function is a very beautiful one because it represents sigmoid. What is a sigmoid function? Can someone tell me quickly? Okay. How does it look? We need to make sure that we are plotting it so that we know, because that's the real beauty of this function, right? Can someone tell me how a sigmoid function looks? It's also called an activation function. Basically, what it will do is, what will it do? It will basically either make it 0 or 1, whatever the number. So let's say if there's numbers between 0 to 1, it will transform it to 0 or it will transform it to 1. Marks deducted. Right. Cool. So let's look how it might look. So can we whenever I look at a function, the first thing I'll probably do is let me just put x equal to 0. So I'll just understand where would the fx be or y be, right? So x equal to 0, e to the power minus 0, e to the power 0 is basically 1. So 1 plus 1 is 0.5. So y, or let's say sigma x, x equal to 0, sigma of x becomes 0.5, right? If I'm not wrong. So it will be here, 0.5 or y. So basically, if this is maximum, this is 1 and this is 0. So I can have a curve which looks like, oh my god, my drawing is pathetic, which looks like this. Okay, I'm trying really hard to draw this, but yeah, it will converge actually. So yeah, I've tried really hard to do this, but okay. So we'll have yeah, S shape. That's correct. Yeah, this is a S-shaped curve. It's called the sigmoid function. Okay, and you can have values here which will be 1 and values here which will be 0. Okay, so let's try to move on now. Like, this is a sigmoid function. I just wanted to tell you guys how it will look. So I just wanted to make sure that you guys are able to understand, right? We did a lot of math and we tried to we did the equation of a line, we did the cost function, we did r square. So the formulas are very easy. We also did gradient descent. We are looking at sigmoid function right now, and we also did the derivation right now, and then we can do the evaluation, right? So I hope you like the derivation. You saw the sigmoid function, and if you, I probably have a slide for sigmoid function as well, so it will look nice, much better than my drawing, I guess. So let's look at what time is it? Is it 8:30? Oh wow. Okay, guys, I think we should probably close off in a bit, because if I can keep going, I really underestimate the amount of content I made for 2 hours, right? So I probably am going to close after logistic regression. I can do the code in part 2, because let's start with the logistic regression code here, and let's take up some questions and everything, right? Why is this drawing like this? Anyway, so you can see that we cannot use a linear model for these kind of problems. We need a logistic model. So this will be the probability of a, that will so it will basically calculate the probability, right, which is 1 by 1 plus e to the power minus, we just did the derivation for that, right? So we'll probably go to decision trees and everything. I will create a separate part 2 for that, but please stick around, because I'm going to do the conclusion here and also take questions, because Yeah, right. Let me skip to the important one. Summary. Okay. What did we do? We studied the data. We selected a model. We could have done decision trees. We could have done random forest. But yeah, we did part one today. I'm going to do the part two next week for sure. Uh, we selected a model. We trained on training data. We did the learning algorithms. We did the derivations. So basically, the algorithm searched for the model parameters that minimized the cost function. Right? We made predictions. That was called inference. You already saw this word cloud, so there's no surprise here. This is a meme that I got and I really liked it. So I thought I'll share this with you guys. So a lot of people say that, hey, let's use deep learning for this. Let's use some advanced technique for this. You don't really need deep learning, right? You just need. Okay, next class is going to be next Sunday, and please do join. And it's going to be technical as well because I want to complete decision trees, random forest, and we look at code and example and obviously the math. So let me conclude this class and then we can talk about it. Okay. So you don't really need to use deep learning for a simple problem. And this is also a meme that I really liked. So you have to work a lot when you're doing statistical analysis, right? And when you are using neural networks, you really don't know what's happening behind the. So that's why it's called a black box. And right now, researchers of AI, they're trying their best to understand what's going inside this black box. How is this model learning? How is a neural network model learning, right? So that's why it's a funny meme from 5 years ago, but I still think it's valid for people who for people who want to, like, I'm just going to take a couple of minutes because there's 27 people who are still here, especially for you guys. Okay. So right now we are doing machine learning. This is the path that I want to follow. If you're thinking that I'm trying to make a series, I will follow this path. I will do everything possible in machine learning. We'll have the base. We'll learn together. It's not like that I'm teaching you. I am learning from you guys as well. You guys are the ones who are supporting me so much. I will make sure that I come with the best materials and the best resources. Okay. So we learn machine learning first, and then we'll do deep learning. So in deep learning, we'll go to autoencoders. We'll do artificial neural networks. We'll try to get more data. We'll understand why deep learning is required and why is it better. Like, it's going to be much more mathematical, and we'll try to understand what neurons do and stuff. I would recommend you guys to watch Introduction to Deep Learning by MIT. I really like that. I've been watching it on YouTube. It's freely available. Then we'll move on to NLP, and then we'll finally move on to LLMs, right? If you want to do LLMs, in between there's something called attention is all you need. So I will try to discuss the entire research paper of attention is all you need and why transformers work the way they do. What is the attention mechanism? So that will require a lot of time, but I'll make sure that I have an intuitive understanding of it, that I can explain the math even better. And these are really hard things. So if you guys have stuck around till now, 27 people, you realize that 47, 50 people joined, and now it's just 27 of you guys who are here and listening to me, that these are really hard things. You are actually the true builders of AI who are interested in doing all these things. And, you guys are interested in knowing the fundamental foundational mathematics behind all these things. That's why I want to go in a sequence. This is my vision. I don't want to teach people LLMs if they don't know statistics. Like, I don't know how I'll explain certain things to them. So I want to make sure that we go deep into the maths, and then we, then we'll basically cover more advanced topics. So if you learn with me, probably in the next 6 months, we're doing like cutting edge AI research. And people who will be joining me later, which is like when I do LLMs or generative AI, they'll be like, oh, wow, you're doing generative AI. But they wouldn't understand the foundational knowledge to understand this. Like, gradient descent is a very important algorithm that every machine learning engineer must know, right? So in LLMs, there's different things which we learn about. We'll do the math and everything, right? Okay, so I'll give you a prerequisite of the topics in mathematics that are required to learn. So basically what I would suggest is like you start with the maths. So you start with statistics, you start with probability, linear algebra, differential calculus. Okay, is there anything else that that we need to learn? Probably not. And then you do move on to programming skills. Learn GitHub, learn DSA, basically learning how to use different data structures and algorithms, play around with data, do some data science, right? And if you have any questions, if you guys spent the last 2 hours with me, if you guys have any question, I'm going to post a LinkedIn post right now, and you know, feel free to communicate with others, with other learners, and you know, speak to them, connect with them, what they're learning about. Feel free to give me feedback and tell me how I can improve. And Radhika is telling me to sing sometime as well. For sure. Thank you so much for appreciating that. I will definitely be singing some song someday. But first, we have to understand that we need to make sure that we understand all these things, right? We have to understand the math as well. So thank you so much for joining. Thank you for spending the last 2 hours with me. I hope I was able to understand. I hope I was able to make you guys understand the foundational intuition and math behind gradient descent, why linear regression works, when it wouldn't work, and logistic regression. I'm going to have a part 2 of this where I'm going to probably take up k nearest neighbors and gradient boosting, and I will have more time, right? So I'll probably take up something else. So this was part 1, and in the next part I will discuss about decision trees, random forests, k nearest neighbors, and gradient boosting, or anything else which we have probably skipped, and probably take a real world example as well. In that I can walk you through each and everything. Okay, so I hope this was a good one. Congratulations for completing it, and I am going to stop sharing and speak to you guys directly. So thank you for sticking around. Thank you for, even if it was like 5 people, 10 people, I would have still done it with the same energy because I'm really interested in learning. And let me stop the recording now.